Can you hear me?
Yes, we can hear.
Okay, I hear you, but somehow I can't find the chat. The chat's gone away. Okay, there it goes. Now I'm back to where I should be.
Here we
Okay. So I think I'm set up. You can see this, you see the desktop? Everything seem ready? Okay. Gonna keep talking about closures today. And where we left off on Monday is that we had language 8 and we were looking at the evaluator for language 8. Okay, now let me just remind you where we were, but then I want to do something else and then go back to where we were. So where we were was we have to, the thing about language 8 is that lambda and apply are different, okay? The main thing is that lambda and apply have changed. Fun now just acts like a version of var. That's what we did on Monday. But the real heart of it is that lambda and apply have changed. They're going to make use of these closures. So we want to look at the code for lambda and apply to see what's different. Okay. Okay. And we did lambda, and we're actually where we left off was we were starting to talk about apply, which is the real how do you call a function using a closure. That was the real core idea. How do you call a function using a closure? Okay. Now, before going back and doing that, I want to look at some more examples of closures to show you some kind of interesting ideas. And getting a sense of what closures are goes a long way towards trying to help understand how they get implemented. So I've got, this isn't up on the website yet, but I'll put it up there after class. I've got some examples in Java, language 8, and in Racket. And I actually wanted to do them in JavaScript too, but I didn't have time. In the next couple of days, I'll do these in JavaScript also, because JavaScript has closures. Okay, so here's the example. This is the example we've done already. Here's make adder, and here's make adder in Racket. That's the one we've done. We've done this one a lot now. Okay, so we've done. Let's see. We've done this example. The Racket and the Racket version and the language 8 version look very similar. So that's the Racket version. This is the language 8 version. Okay, and this one's the Racket version, and they're pretty similar. There's not a whole lot of difference between them. Okay, now the key was that you have a lambda that's returning a lambda. So you have a function that's returning a function. The function is nested inside of it, okay? One thing that's kind of nice is if we run this in our language 8, okay, now I put an interpreter for language 8 in this folder. See here, I got a jar file that is an interpreter for language 8, okay? And if I open up a command window here, I can run my program just as like if it was a real programming language. So I can say the language 8 interpreter, I want to interpret the make adder program for language 8. Okay, and it ran it. What I want to show you, what's interesting is to look at the notation. This is the pretty printed version of it. Look at it from this point of view. This is like a C-like notation for the function, and compare it to the Java and compare it to the Racket and the Lambda 8 language 8. So this is written in Lisp notation. This is written in Lisp notation. Here's sort of here's what it would look like if you wrote it. The JavaScript version that's why I want to write this in JavaScript. The JavaScript version will look a lot like this. We have a program that has a function called make adder. Make adder takes in X, and make adder returns a lambda expression. So make adder returns the function that takes in Y and adds Y to that X. So there's the function that returns a function. Then we call the function with a parameter and give a name to the function that it returns. So add 4 is a name for y goes to x, y goes to 4 plus y. So because that 4 got stored in x, and so essentially this is y goes to 4 plus y. Then you call, okay, the key idea that when you look at this code, the key idea is who keeps track of that x? When you call make adder and you pass it 4, x is 4. Then you return this thing. How do you keep track of the 4? Okay. And I'm going to eventually I should tell you that there's actually 2 ways to keep track of the 4. Okay. And what we're doing is called closures. Java actually does this in a kind of odd way that isn't quite closures. So we want to actually look at what Java does with this thing. Okay. So we want to look, yeah, it's at when it's written this way, it's when it's written that way, it's actually kind of a nice thing to look at. I mean, it's kind of nice to look at it from the point of view of this is essentially what this is close to. It's more or less like JavaScript. Okay. Okay. I'll actually pretend that this is JavaScript. Okay, it's not really JavaScript, but JavaScript's not going to be all that much different than this. Okay, so yeah, I've got 3 versions of this program now. Okay. Okay. And from the point of view of the way you're used to, this notation's weird. I mean, I'm very used to it because I've been using it for a large chunk of my life, but I do remember well how hard it was to get used to this notation. It's got a beauty to it that's really, there's a real beauty to it, the fact that essentially the notation is an abstract syntax tree, which gives the language a real power. But it is kind of hard to deal with it, But on the other hand, this is the direct translation of it into the kind of language we're used to. So there's a function that takes in a parameter and returns another function. Notice I'm using 2 different notations. I'm using a traditional notation for the outer function and a lambda notation for the inner function. Okay, and that works out pretty well. So function make adder takes an x and returns a lambda expression that takes in a y and adds y to x. Okay, the key question is who's keeping track of x for you? Okay, now let's look at the Java version of this program. Okay, I wrote this program in Java. Of course, the Java version is going to be ridiculously verbose. See if I can get them all, kind of get them all in here. Almost fit. Okay. Let's see, maybe. No, that's not going to work either. Okay. Wow. See the okay. Well, okay. There's the Java version. There is. Let's just not use all 3 of them, all 4 of them. So let's. I've lost my mouse. Oh, great. The battery. I think the battery's dying on my mouse. Okay, there it came back. Okay, so let's just look at 3 versions. Okay. This is the easiest one to read. Make adder takes in x and returns this lambda expression. Okay, same thing here. This make adder is a lambda that returns a lambda. Okay, now look over here. Make adder is a function that takes in an integer and returns a function that takes in an integer and returns an integer. Okay, so since Java is a typed language, I have to tell you what make adder does. So I have to give a type to make adder. So make adder is, okay, make adder has that type. See, this is the verbosity of Java. I have to give you a type for everything. So the type of make adder is a function that takes in an integer and returns a function that takes in an integer and returns an integer. Okay, so it's a very nested generic type. And then I have to import the predefined function type. Okay, so I import the function. The java.util library is a collection of predefined function types. And we're using the function type called function because it's the simplest. The function type called function is a function that takes in one argument and returns another argument. And our function make adder takes in one argument and returns another argument, which is a function that takes in one argument and returns another argument. Okay. But then what does make adder do? It takes in x and returns a lambda. Okay, so there's that notation right there. See, there's that notation right there. But here, over here, I'm using a lambda notation for both the outer and the inner function. Okay, so actually, maybe I shouldn't. I can actually make this. I don't know if I can get away with using. I'm not sure if Java is going to like this. Now I've written it very much like this one here. Okay, make adder takes in an x, make adder takes in an x, and what does it return? A lambda expression. See, there's the lambda expression.
I've seen that syntax used in some pretty advanced examples, but I don't know enough about it to say whether or not you did it right.
Yeah, I was right, and I think I switched it from being a lambda expression to being a traditional function. So I switched. Let's just try it. Let's see, compile it.
Oh.
Yeah, let's see what was. Now maybe I need to put the type.
You need a return type.
Yeah, since I'm using the traditional notation here, I probably have to. I have to give it a type here. And I probably have to say return here.
Return type. You need a return type in
this function. Well, no, make adder does have a return type. See the trouble. There's its return type.
But you are not returning anything. Now you are returning.
Yeah. Well, I'm returning that lambda expression.
Mm-hmm.
Let's see.
I think you have to have a semicolon on line 10.
On line 10? No, because that's the beginning of an expression.
No, it is not required.
See, the trouble is, Java's, let me think. Make adder, okay, so let me peel off one of these. Let me try this. Make adder takes in an int and returns a function of one variable.
Maybe you need a semicolon on line 13 then to say that that's the end of a statement.
Yeah, yeah, it's required.
Nope, it still doesn't like it.
That's the trouble with trying to do Java on the fly. Java's become a very messy. Java has tried to add lambda expressions to the language after the fact, and they've ended up with something pretty ad hoc. Now, notice this makes sense. Now, it very much looks a lot like this, but Java's not liking it. There's the function. There's its input.
What version of Java are you using?
You have to use Java 8 or later. To do
Minimum
this.
8.
Let me see
Yeah.
if my Java book has anything about this. It might not be. It might be too old. Nah. My book uses Java 5. Not gonna help.
I think the problem is that Java does not allow nested functions using this notation. Java
I swear
only,
I've seen that notation though.
well, yeah,
But I
for
think it defined them.
anonymous
Yeah, it
inner
used them
classes.
anonymously.
Yeah. I could try. Well, I'm only down to one error now.
Cannot find symbol make adder.
So now I have to.
That's odd. You would need to give it a function argument, like an argument right after the name function or make adder, because it's a function call.
What?
Hold on, annotate.
Adder?
You
Has
need
type.
a argument right here. Do I have white?
No, I don't see.
I might have white text, or yeah, there we go. You need a argument right there. Oh God, that's hard.
Yeah, I should.
Because make adder is a method.
Oh, because I changed it. It's not a Lambda expression anymore.
Mm-hmm.
Well, okay.
You'd also need to define this as static.
Yeah,
Otherwise, it's gonna yell at you right after you fix that.
Yep. And now. Okay, and this is. There it goes. Okay, but this is not what I wanted. See, now it's starting. Now this is written in a more old-fashioned style of Java, and well, you know, it is. This is written now in a more old-fashioned style.
It is spitting out a lambda that has to be closed.
Yeah. Mm-hmm. Yeah. I mean, it is doing what we want. It's not. We can't write it in this nested style. Okay.
Java just won't let you do that.
If I run it, see, it returns the right thing. 9. See, it created this creates this. We call make adder with parameter 4, and it returns that lambda expression to that variable there. Okay. Now here, let me do something.
You might be able to get away with this if you define.
No, we did get away with it.
No, I mean like do it nested if you define make adder as a class.
Right. There's okay. Let me just save this.
But yeah, looking at this stuff, it's looking more and more like Bash, with how arcane some of the stuff is getting,
now,
which is
let me
not
go
good.
Back, let me go back to what we started with, which was the elegant. There's what we started with. So this is the real elegant, ultra modern way to write it in Java. Okay. Here's the kind of unelegant, old-fashioned way to write the same thing in Java. And there's other ways to write this in the old-fashioned way too. And so this still uses a lambda expression. So this is kind of a mixed. This one here is like a mixed bag. It's using a little bit of modern notation, and it's using also the old-fashioned notation of making this a static function. I could make this a static nested inner class inside here, which is, that's the way I want to write it. I'll figure out the syntax for that later. But this is the ultra modern way to write it. Okay. Now, if you look at this, this, or this, you can come to the conclusion that Java is doing the same thing that JavaScript, that Racket's doing. But it turns out it is not. What Java is doing over here is cheating. It is not creating a closure the way we're going to define closures. Okay, Java is not really doing on the left. It doesn't matter if you write it this way or write it this way. Okay, right now this code mimics exactly this code, but the implementation of this code is not at all like the implementation of this code. Okay, so what I want to do next is go to another program that shows you that Java doesn't work like Racket or like our language 8. Okay, so now I'm going to switch to another program. Instead of doing make adder, we're going to do make counter. Okay, so let's do it in Racket and language 8 first, and then we'll look at it in Java. Okay, make counter is just like a little variation on make adder. Okay, so this one is language 8, and then down here is the Racket one. It's only a little bit different than make adder. What make counter does is it takes in x and it returns a lambda that takes x, increments it by 1, and then returns the new value of x. Notice that this lambda doesn't take in any parameters. It's a void function. It doesn't actually have any parameters. So make counter takes in a lambda. Make counter is a function that takes in a parameter, and it returns a function of no parameters that increments the x and returns it. Okay, so this one, x is the initial value of where you're incrementing up from. So if I apply make counter to 4, I'm creating a function that counts from 4. Okay, so this is a function that counts from 4. If I call it with no parameters, it'll return 5, then return 6, then return 7. Okay, here's the Racket version of it. Make counter is a lambda that takes in 1 parameter. It returns a lambda that has no parameters. Notice it's a little bit easier to read this. The empty brackets tell you that there's no parameters. Here you had to be kind of sneaky and realize that there's nothing between the lambda and the parentheses, so there's no parameter there. Okay, so it returns a function that doesn't take any parameters, and what it does is it mutates x to be x plus 1, and then returns the mutated x. In Racket, the set does not return a value, whereas in our language, set returns the new value of the variable. In Racket's language, set is not an expression. It doesn't return a value. So after you mutate x, you have to return x. Okay, then you make a counter starting at 4, so it's called count from 4. Then you call this without any parameters, and you'll go 5, 6, 7. Okay, let me run the Racket one. Racket's real slow to start up. This always amazed me how slow Racket is. This Dr. Racket is to start up.
Just the Racket REPL on Linux starts up instantly.
Yeah, on Java too, on Windows too. The Racket REPL's this one here. It starts up immediately. Yeah, but the Dr. Racket takes a little while. Okay, so here's Dr. Racket. Now if I just run this, you see it produces 5, 6, 7. Okay, so it's counting. Now count from 4, now 8. How do I get the? I don't remember how to get the history list in Dr. Racket. If I hit up arrow, I go up. I go up. Okay.
Huh.
Yeah.
Control up?
I don't know. I thought that, let's see, control. Yeah, control F is the history list. Good. Yeah, Control F.
Okay.
Control F is the history list. Okay, so see now I'm counting. See, I'm counting. Okay, 12, 13. So I started at 4. I started at 4. So the first time I called count from 4, I get 5, 6, 7. So this X, now notice that this is really weird here. What's happening is that X, whoever's holding it, is being changed every time I call count from 4. That X, wherever it's being held, whoever's holding it is letting it be incremented. So
Did it increment when you bound it to a name, like a new name, and closed it?
I didn't bind it to a new name. It's always X. See?
Oh,
It's
no,
just
no.
X.
What I meant was when you ran define count from 4, make counter
Mhm.
4, did it increment to 5 when you did
No,
that?
no,
Okay.
because this doesn't evaluate the body of the lambda. This
It
just returns the
just
lambda.
binds it.
Yes, yeah, it binds it to 4. X is bound to 4.
Okay.
Okay. And then since I'm doing a pre-increment, the first time you call it, it goes from 4 to 5. Then the second time you call it, it goes from 5 to 6. So the first time we call it, we get back 5. Okay, because we're incrementing it and then returning it. So it's essentially a pre-increment. We're incrementing it and then returning it. Okay, all right. Now I can also run this in my language Java 8. To run it in language 8, I'll call up a command window, and I do language 8 command. I'm running, the language 8's buried in this jar file. The jar file's got the whole interpreter for language 8 in it. I want to run make counter language 8. Okay, and you can see that it gives you out a lot of, see there's the 6, 7, let's see, it should give me 5, yeah, there's 5, 6, 7. Okay, here's the program printed in kind of, let me, here's the JavaScript-like version of it. Okay. Notice that you can see kind of nicely here. It's a function that takes in one argument and returns a lambda expression that doesn't take any argument. So the lambda expression doesn't take an argument, but it sets x, it mutates x. It returns the thing that takes x and sets it equal to x plus 1. So it returns an incremented x. Okay, so then you create a copy of this that starts with x equal 4. This one starts with x equal 4. Then you call make counter. Notice that it's being called with no parameters. See, it's being called with see, you call make from count from 4 with no parameters. And each time you call it, it remembers the previous value and prints it. Now, if you remember your C programming real well, you know that the C language allows you to have functions with static variables. So you can write this in C, but in a really weird way using a static variable. Okay, but you can't have two make count. You can only have one version of this. If you do this in C with a static variable, you can have only one make counter at a time. You know, like here, I could do this. I'm allowed to do this. I could have two of these at the same time. And I could think about what that's going to return. Think about what's that's going to count from 4 and return 5. This is going to return 7. And this is going to return 6. And this is going to return 8. And this is going to return 9. And this is going to return 7. Okay, because there's going to be 2 instances of make counter, one counting from 4 and one counting from 6. And then you can, this one keeps track of his initial value, and this one keeps track of his initial value. You can't do this in C. If you try to write this make counter in C, you would only be able to have one of these at a time. You could either have him or you could have him, but you can't have them both at the same time because each function can only have one static variable. Maybe I'll even write a version of this in C so you can see what I'm talking about. It's not using closures at all. Static variables are kind of a weird idea that C can use. In a sense, you might say that static variables in C are like a really poor implementation of closures, but you'll see that there's a limitation to what they can do compared to this. Okay, all right. So now let's look at the Java version of this program, and it doesn't work. Java actually cannot write make counter. Okay, so here is, we clean up a little bit. Here's the Java version of what tries to be make counter. Okay. And let's look at it. It looks like it looks just like what the ones we were doing before do. Okay. So what is make counter? Make counter is a function that takes in an integer and returns a function, no variables, that returns an integer. Java calls that an int supplier. Okay, in Java speak, an int supplier is a function that takes in no parameters and returns you an int. Okay, so that's this guy here. That's a function that takes in no parameter and returns an int. That's called an int supplier. Okay, so make counter is a function that takes in an integer, that's this guy, and returns an int supplier. That's this guy in here. I wonder if I need these extra parentheses. I don't know if I may not need that. Well, we'll try to figure it out later. Okay, all right. So there's int. Okay, now I call make counter with value 4. Okay, so that should be count from 4. And then okay, when you have an int supplier, you call it by calling get as int. So notice that you don't call the function directly. That was actually true of the other one too. In the other Java version, notice that you didn't call this function directly. You had to apply, just like in our language, you have to have this verbose, you have to say apply this parameter, apply this function to this parameter. Java doesn't let you just call add 4 with parameter 5. Because of the weirdness of the way Java works, and kind of like what we had to do, they had to have a little bit of extra verbiage. So you say apply this function to that argument. Okay, so here with the make counter, oops, I would say get as int this function. That's going to call this function with no parameter and return its int. Okay, but if you compile this, you get a weird little warning. It won't compile. And this lies at the heart of what's really interesting in all this. In Java, essentially, when something is acting like a closure, the variable it's closing over has to be a constant. You can't close over a variable that's being mutated. Now, over here, the variable we were closing over, the free variable in this lambda, the free variable is x. So that's the variable that we're trying to close over. We're trying to close that x with this environment outside of it. But notice that we never change x. Once we give x the value 4, it stays 4 forever in this example. So this is essentially acting like a constant. Once it's been given, it's sometimes called a write once variable. You put 4 into x and then it never changes. So Java calls it effectively final. Java has see the phrase down here, effectively final. This is effectively final. Once it's given a value, that value never changes. Over here, X is not effectively final, and Java says I cannot close over. See, local variables referred to from a Lambda expression must be final or effectively final. What Java's saying is its closures are limited. They can only close over constants or things that act like they're effectively final, meaning that variables that once they're given a value, they never change. Okay, so Java's closures are now watch this. If I take away the plus plus, so it's no longer being mutated, it compiles and it runs. See, but see now it doesn't mutate, so it's not counting from 4 anymore. See, now it's just going to return 4 every time. So now
could you instead have it spit out a new function object where in that version of the new function it's incremented?
Probably, but that's not the key. I want to say, how does Java compare to Racket? So the question isn't, can I do this in Java? The question is, like, how does Java differ from Racket and language 8? This is the code that looks exactly like Racket. And what we're seeing is that Java doesn't act like Racket. It is not a functional programming language.
It's just doing value substitution.
Essentially, yeah, it's what it's really doing is, okay, remember I said that there's going to be 2 ways that you could capture this non-local reference. Okay, now the words we're going to use are closures and non-local references and capture. In this Lambda expression, we have a non-local reference. The Lambda expression is not closed. We need to close it with something. We need to close it with this guy. There's essentially 2 ways you can close this guy. You can bundle him with a copy of X, or you could point him at the environment that holds X. Okay, those are the 2 ideas. You could bundle the Lambda expression with a copy of X, or you could point the Lambda expression at the environment that holds X. Okay. Java does it the way of 2 ways to the one way is to okay. Okay, here's one way to implement closures. You bundle the open Lambda expression. The Lambda expression has a variable in it that's a non-local reference with a copy of the variable that closes the Lambda expression, okay? That's what Java does. Okay, the other thing you can do is bundle the open okay. Okay, so this is the IPEP pair. You could bundle the lambda expression. So the bundle is the IPEP pair. You could bundle, that's the IPEP pair. You could bundle the open lambda expression, that's the IP, with a pointer to the environment, that's the EP, that holds the variable that closes the lambda expression, okay? That's what a real closure is. What Java does is it cheats. It doesn't point, what it bundles the lambda expression with is not a pointer to the environment, it just bundles it with a copy of the variable, okay? Right? Now,
Why though?
because the language is, when the language was designed, they didn't think they wanted functional programming. And then that kind of caught up with them. So now they're trying to approximate functional programming, but they have to be backwards compatible with all the code that was written in the past. So this is as close as they can get to functional programming without breaking old code. So they're stuck with not satisfying anybody. Yeah, they're a bad approximation of functional programming. Well, they're a bad approximation of functional programming, and they do not break old code. Okay. Okay. Now, go back and look at this code, and if you think about it, there's still something that's not kind of. Suppose I bundled this with a copy of X. Okay. Why does that, that alone doesn't mean that this isn't going to work. Because what that would do is then you could mutate the X that's bundled with this guy. Okay. So what you're going to do is you're going to bundle him with a copy of X. Okay. Let me think. What's wrong with that? I'm sorry. I get, okay, now I remember. Okay, so what Java does is take this lambda expression here and bundles it with a copy of X. Now that begs the question, well, why not mutate the X that's bundled with the lambda expression? Okay, and the answer to that is you have to do more complicated example to find out that's a bad way to do it. It actually would seem to be okay in this example to just say, well, okay, this lambda expression can just mutate the X that's copied with him. But then if I wrote a more complicated example, and I probably should do one, maybe I'll try to think a good one. But if you do a slightly more complicated example, you'll realize that that's a bad answer. It won't give you the right answer. It won't work correctly in many programs. Okay, so you can't, so what Java does is it bundles a copy of X with this lambda expression, but it makes the X read only. It makes it a constant. So it works okay if I do this. The X is a constant 4, but it doesn't work if I do this because the 4 is a constant. The X is a constant, so it cannot be mutated. Okay, so Java, if I go back over here to this, bundle the open lambda expression with a copy of the variable, but that copy with a constant copy of the variable. So that's the thing. Java makes it a constant copy of the variable. And it's that constant that's actually kind of the tricky part. It's not so obvious why it has to be a constant, but it does. If you didn't make it a constant copy, it would work. It would be okay for this example. It would work. But a more complicated example, things would start breaking down. The language would stop I should come up with an example to show you why you would not want to make this a non-constant copy and just let the Lambda expression mutate the copy. Okay, so you bundle the open Lambda expression with a constant copy of the variable that closes the Lambda expression. That's what Java does.
What if you gave it a object that you could mutate in place?
But yeah, that's what people do.
Oh,
But see,
okay.
then it's not mimicking functional programming. Yeah, and then but then you have a lot of overhead. You have to write a lot more boilerplate code. You have to write that.
Mm-hmm.
See, so that's exactly what Java originally thought you should do. If you wanted to write something like this, okay, I could write this program in a very classical Java way. Well, I should do that. Eventually, we'll do this in a bunch of ways. The very classical way to do this is to have make counter create a counter class that holds the initial value, and then it's got a method in the counter class that does the incrementing. And for a long time, the Java people thought that they had really hit a home run. They thought they'd found a way to be able to do a lot of what functional programming did with object-oriented programming. But then eventually, over time, they realized it wasn't as good a design as they thought it was. Functional programming turned out to be more elegant than what Java had come up with. But that's, the Java version of this should be rewritten a bunch of ways to show you all the different styles that Java's gone through. Yeah, like this, the make incrementer works okay in Java. Okay, make adder, I'm sorry. Make adder works in Java, but I should still write this in the old-fashioned Java way to let you see how Java originally thought this kind of a problem should be attacked. That old-fashioned way would work here, but this one cannot do the more modern way, whereas this one can be this one's written exactly like Racket. Right now, this is Racket, but it's using the fact that this X is never mutated. But as long as the X is never mutated, Java does look like a functional programming language, as long as you don't try to mutate these guys here. But as soon as you want to mutate them, then Java no longer looks like a functional programming language. But you can still do this using the old-fashioned style of Java programming, using objects instead of, remember we said that objects are poor man's closures and closures are poor man's objects?
Yep.
This is where that dichotomy comes in. I could redo this one using real object-oriented programming, but then it's just not functional. And then you get debates about which is really the more elegant style of programming, object-oriented or functional. And what people are leaning towards now are languages like Scala and Clojure, which really truly combine object-oriented programming with functional programming. Okay, Clojure and Scala that try to really that do Java 1. Now, both these languages run on the Java virtual machine. They're both Java virtual machine languages, and they both essentially try to fix this problem of Java not really integrating the functional style of programming with the object style of programming very well. Scala really, that was Scala's design goal, was to support functional programming and object-oriented programming together. Clojure, not as much so. Clojure does functional programming real well, and I think it does a little bit of object-oriented programming. I think Clojure's main goal was more leaning towards functional programming. Scala was trying to be very much both, a blend of functional and object-oriented programming. Modern Java, which is what this guy is written in here, this one here written in very modern Java, is trying to get Java to be as close to functional programming without breaking old code. Okay. So, so now we've got these two senses of how you could build a closure. Again, by just copying the variable, but you have to make it a constant copy, or by an IP-EP pair. The IP-EP, now see, when it's an IP-EP pair and you've got a pointer into the environment, that's a lot like what you would do in Java when you built these things with objects. The object holds a variable, you point at the object, which in this case is the environment, and then you mutate something inside the environment, which is like mutating something inside of an object. Okay, so this one is very much kind of, it is very close to being object-oriented programming, because you have this object called the environment that holds the variable that we want to mutate. Okay, and as long as I hold a pointer to that environment, I can mutate the variable all I want. Okay. Okay. So now let's go back. One last thing is, think about these examples. Try to make sure you understand why Java blows up on this one. But it's okay if I make this this little, like that, it's not interesting, but it compiles and runs. This doesn't work. Java is doing closures in a kind of bad way. So the closures have a limitation that they can only close constants. Okay. Whereas Racket and Scheme and Language 8, they all do closures in a much more interesting way, so that when this variable is in, when you refer to this variable in the closure, this set mutates that variable. You're allowed to mutate the variable in the closure. Okay. Oh, let me show you one last thing. If you Google you get some real interesting things here. According to the official definition of the Java language, it claims to have closures. Because it does close over a open Lambda expression. See, remember this guy. Okay. Java can, not that one, I'm sorry, this one, make adder. Java can close over that open Lambda expression, right? So Java has closures. And according to the official definition of the Java language, it does refer to these as closures. It is closing over an open Lambda expression, a Lambda expression with a non-local reference. But we know now that that closure has got a real limitation to it. It can't close over something that tries to mutate the closed variable. Okay, so then you ask the question, does Java have closures? And you'll see a lot of people saying, no, it does not, because of this limitation. But it's, you'll also see people say it does have closures. So you see a debate go on here. You actually, are Java 8 lambdas closures?
Aren't mutators generally frowned upon in functional styles anyway?
Yes and no.
Oh boy.
Yeah. What I just wrote here would be really hard to write in Haskell.
Yeah, I
This
would
make
argue
adder?
you just shouldn't.
Well, no. You can, no. You can do this in Haskell. You just have to be more careful about it. So make counter, which mutates this variable, can be written in Haskell, but it's a little bit harder. Notice that Scheme makes me work a little bit. Remember, like Scheme does not return a value from the mutator. That was Scheme's way of saying, we wrote our set to return a value. So our mutator returns a value. Racket says, if something is a mutator, it doesn't return a value. So we had to return the value after we mutated it. That's Racket's way of kind of tapping you on the shoulder and saying, mutators are weird. You should probably maybe not use mutators. But notice that Racket makes it easy to use one. Haskell actually makes it hard to use mutators. But you can't.
I remember that.
Yeah, Haskell lets you use them, but you have to jump through hoops to use them. Racket lets you use them without much trouble at all, but the mutator itself does not return a value. which is a little bit of a hint that a mutator is kind of different, okay? There's plenty of mutation in functional programming, but yeah, you do less of it. You don't use as much mutation as you do in imperative stuff in traditional procedural programming, okay? Okay, but so closures that want to mutate the thing they're closing over are reasonably common even in functional programming languages, okay? All right, so Java has closures. This program proves that Java can do a closure, and this program proves that Java can't do the same kind of closures that Racket can do and Scheme can do. So you get a debate on the internet. Does Java have closures? Okay, and you can make a good argument for yes and no. Yes, it has closures, but they're a kind of closure. They're not the same kind of closure that Scheme has, okay? So it's kind of interesting to, if you read this, you'll see a lot of back and forth about people arguing about does or doesn't Java have closures, okay? Okay, all right, now let's go, let's go back to the interpreter to kind of look at how this stuff could be implemented, okay? Okay, so the real key was, what do you do when you want to apply a function, when you want to call a function? Okay. Now, we know that when you apply something, what you apply is a lambda. And we know that a lambda is really not just a lambda, it's a closure. Okay. The lambda now is a lambda expression bundled with a pointer to the environment that closes the expression. Okay, now not every lambda expression is open. So when a lambda expression is already closed anyway, when it doesn't have any free variables, you still have an environment pointer. It's just not very useful at that point. So a lambda expression in our design here, a lambda expression is always an IP-EP pair, but some lambda expressions don't need the environment pointer part of it, but they always have it anyway, okay? If the, we'll see what they point to, okay? All right, so the lambda expression always is, it's the a lambda value, I should say, a lambda expression is this. A lambda expression returns a lambda value, and a lambda value is an IP-EP pair. See, a lambda value, when a value has the tag lambda, the value actually is holding an IP-EP pair, and an IP-EP pair is 2 pointers, a pointer to a tree and a pointer to an environment. Okay, because Java reference variables are really pointers. So I call it an IP-EP. I could have called it an IRER pair for an instruction reference variable and an environment reference variable, but IRERs are not, you won't find those mentioned anywhere in the world. You will sometimes, people see, people do use the IP-EP pair notation occasionally. It's an old-fashioned name for these things, but I think I like the fact that it really tells you what they are. I mean, if I was being more modern, I'd call this class the closure class. Yeah, but then, then you kind of go, what is a closure? Because you see this all the time. People, well, what are closures? What are closures? You see these people Google on Stack Overflow. There's probably 1,000 questions asking what closures are. So I kind of like calling it IP-EP because it's an old-fashioned term, but that's what it is. A closure is 2 pointers, a pointer to the code you want to execute, and a pointer to the environment that closes any of the open variables in your code, okay? So a lambda expression returns a lambda value, which is an IP-EP pair, okay? So then you apply lambda values. you actually, when you call a function, you apply a function to its arguments. This function should evaluate to a IP-EP pair, okay? See, the function value is the first expression. It should be the result of a lambda expression. It should be a IP-EP closure. So this guy should evaluate to a closure, and then this evaluates to the parameters of the closure. Okay, that's what we want to look at. The code that takes a closure and a bunch of parameters, and then runs the closure on those parameters. Okay, so we go down here. Okay, here's evaluate apply. Okay, we are applying let's see. We are applying an IP-EP pair to a bunch of expressions that are the parameters of the IP-EP pair. So what's really here is an IP-EP hit. We're applying the tree here is a value that holds an IP-EP pair, and we're applying it to expressions. Okay, so this guy is if I spell it out, it's a tree pointer and a environment pointer. Okay, so we're applying a tree pointer and an environment pointer to a list of expressions. Okay, now what we're going to need to do is get the tree, get the environment, then go through these expressions, and the tree holds the actual parameter, I'm sorry, the formal parameters, and these are the actual parameters. Okay, so these are the actual parameters. We have to match up the formal parameters in the tree with the actual parameters. Now that's before we need the environment. We won't need the environment for that purpose. Okay, so we're going to first go through the tree, see how many branches it has. Those are the branches that are the formal parameters, and we match up each formal parameter with one of these expressions. Okay, so that's going to be, okay, step one is get the IP-EP value. Okay, step one is get this. Get the function value by evaluating expression 0. So this is the first, I'm sorry, next, it's the subtree 0. So this is subtree 0. You evaluate subtree 0, okay, and you get the function value, the IP-EP pair. Okay, so that's step one. Okay, then step two is build. Well, step two is get this environment. Okay, so you create an environment with the EP out of that function value. We don't need it yet. I could have done these in different orders. So step two actually could have been delayed. Maybe it should be delayed at this point, because step three is actually from a logical point of view is once you have this tree, you'd start matching up its branches with these. Okay, so that's down here. That's step three. You bind in the. Oh, I'm sorry. No, this is the other. I'm sorry. This is the environment. This environment is not that environment. Okay, this environment is the environment that's going to hold the bindings of these actual parameters with these formal parameters with these actual parameters. So this is creating the environment that's going to hold the bindings of the formal parameters in the tree to these actual parameters. Okay, so that's this environment, the local environment. Okay, so you build this environment. Okay, and then you're going to bind then you're going to actually go ahead and start going through these, evaluate them, and as you evaluate these guys, you bind them to a local variable from this tree in this new environment. So you go through the tree and you get the formal parameters, you go through these list of expressions, get the actual parameters, and you bind each actual formal parameter to an actual parameter in this new environment. Okay, that part is the same as it was before we even had closures. Okay, that part's the part that's the same as before. Okay, so this does the binding. These are the steps that do the binding. Okay, now you evaluate. Now you evaluate the body of this tree in the new environment, in the local environment. Okay. Okay. So you evaluate the body of the lambda expression using this environment. Now, where did the closure come in? Okay. The closure comes in back here in step 2. There's the closure. When you create the local environment, you say the local environment is going to point at that closure from here, the EP. The new local environment is going to point to the EP so that whenever something is not in this environment, you go look up its chain, you go into the closing environment. So the local environment holds the actual parameters bound to the formal parameters. And the EP out of the closure is the environment that's going to hold the things that weren't in here, the non-local references. So this is the little trick right here. Okay, this is the trick. If you go back to language 7, oh, I didn't download language 7. This guy was the global environment. Every function was evaluated in respect to the global environment because every function was a global function. So in the previous language, language 7, there's only there's this real minor difference. This was the global environment here, and every function was evaluated in the scope of the global environment, just like in C. If you have a non-local reference in a function in C, it has to be a global variable. The only non-local references you can have in C are to global variables, because that would be, you'd always put the global environment here. Now, the function carries along with him this pointer to an environment that is the environment that closes him. And when you evaluate the function, you evaluate him in this, when you evaluate the function, you evaluate him in this local environment, but the local environment is tied to that closing environment. It's not tied to the global environment, it's tied to the closing environment. And that's the trick. That I think, if I remember right, the only difference between this code here and the same code in language 7 is that this would point to the global environment, and you wouldn't have this IP-EP pair. When you got the function value, it would be just the lambda. There would only be the IP. The function values were only trees in language 7. So there wasn't a EP. So this line would be gone, and this line would be global environment, and that'd really be the only difference. What's amazing is 2 lines of code change you from being C to functional programming. And those 2 lines of code are not trivial. And the proof is they're not trivial is that Java, even when it wanted to become a functional programming language, couldn't really do it. Java had to fudge what it meant by a closure. Java could not really make the change. This change here is so profound that it's not a lot of code. It's 2 lines of code. You change a line of code up here, and you change a line of code here, and that has a profound effect on the way the language works. And that change, that effect is so profound, Java couldn't do it without breaking old code. That change would have been too much for the language. So in Java, this is still going to be the global environment here. Now, what Java does is essentially if you think about what if we were to implement what Java does here, what we would really be doing, see if we can just figure out how to explain what Java does. Okay. Let's look at one of our functions with the non-local references. When you look at the abstract syntax tree of that Lambda expression, you could, like you're writing the analysis program right now, you could analyze it and see that this Lambda expression has a non-local reference. Actually, it'd be better to use the other one. This one's harder to read because it's got a function with no parameters. Okay. When you analyze this Lambda expression, you see that it's got a non-local reference. So then what you could do is when you're parsing this and you analyze it and realize it has a non-local reference, you can just give this Lambda expression essentially another. You basically could just do the following. You could add to it a var x, well, make it var, create a new variable x and give it the value of the x. And then in here, refer to the local variable. See, you could rewrite the code on the fly. And what you'd be doing is copying this variable into that variable, and then basically putting that inside of the Lambda expression. Okay? See, so then this would be evaluated to the constant, whatever this parameter was, and then this would be a local variable holding that constant. Okay? And then you change this guy not to be a non-local reference, you make it this guy here. Now, actually, that doesn't work because that's still a non-local reference here. You have to do it a little bit more cleverly than that. Because now all I've done here is switch the non-local reference from here to here. Well, what you would do is, let me think. I'm trying to think of how Java really does this. I'm trying to mimic what Java does. I can't think of a good way to explain it. You really, we run out of time, but what you really need to do is you need to hard code this for into that Lambda expression. You kind of need a clever way to hard code this for into that Lambda expression. But then when somebody calls this but see, the trouble is you have to do it in a clever way, because if somebody does this, you can't have one Lambda expression that encodes, you can't somehow put a 4 in there, because then it won't work when you call this with 5. You have to come up with a clever way to get this 4 somehow built into that Lambda expression as a constant, and get this 5 built into this Lambda expression as a constant. I can't remember a clever way to explain it, but that's what Java does. Java copies that parameter into the Lambda expression somehow, and copies that constant into the Lambda expression, and it just becomes hard-coded in it. Okay, that's why you can't then mutate it. It just hard codes that value into this thing here. Okay, well, we run out of time. Okay, okay. So yeah, look, I'll make these little versions of here. All these little versions of these code, I'll put them up on the website, and I'll try to add a couple versions of the Java one to give you a sense of how Java's changed from this ultra modern looking Java, how it was done in older, more old-fashioned Java, and and how you could actually do the make counter using Java, but without using closures, by using objects. Okay, so I'll put that code up there. And oh, If you go to this Rosetta Code site, this is just kind of fun. Here's what closures look like in a gazillion different languages. Here's, Rosetta Code, they write the same piece of code in multiple languages. So they're trying to show you what a closure looks like in a whole bunch of languages, okay? I think they picked a lousy example. I don't like the example they picked. I think they should have picked like make adder or make a counter. They picked something weird, but you can see what closures look like in a whole bunch of languages. Like C doesn't really have closures, so they come up with some ad hoc way of imitating closures, okay? I'm not sure quite how they do it, but they come up with some ad hoc way, okay? So it's kind of interesting to see. Now, some languages have closures built into the languages, and some of them you have to fake it, okay? And if you read this thing, they give you a nice little definition of what a closure is. So it's kind of, they give a nice little one paragraph idea of what they mean by closures. So look at that example. I mean, I put those links inside this folder on closures. I'll put that up on the website soon. Okay, so I'm going to go ahead and stop everything. Again, if you have questions, please let me know. And okay, I'm going to end the meeting now. Bye-bye. See you later in the evening, probably.
Right.